So this next unit that we're doing is on kinetics, and kinetics really takes a look at what happens between the time the reactants start reacting and the time that you wind up with products. So kinetics is really like what takes place during the arrow. So there's two major areas in kinetics we're going to take a look at: rates and mechanisms. This video is going to focus on part of the rate aspect, and we'll have other videos that go into different aspects of rates and then also into mechanisms. So rate is really how fast something happens, right? So if you think about it, you can have reactions that happen slowly, like a car rusting. You can have medium reactions like silver nitrate and copper. We were able to do that reaction overnight. You saw it start to happen almost instantaneously. Or you could have something very fast like methane and oxygen combusting, and it's so fast it's explosive with a lot of heat released. So reactions happen at all different speeds. But one thing is true, rate is always the change in some observable property over time. So it could be something like change in mass over time, could be change in color, could be change in concentration, change in temperature, so depending upon conditions and so forth. So change in something per time. We typically focus on concentration, but not always. We're going to do a lab where you're going to see the change in color, which leads to absorbance over time for one of the labs that we do. So what kinds of factors that can affect rate? So there's two ways that we can do it. We can alter the rate by changing the number of collisions. So what's involved there? Well, sometimes it's simply a matter of what kinds of reactants are involved. So the mechanism helps control the rate. If the mechanism is very complicated, the way things have to react is very complicated, obviously it's going to be slow. If it's a more simple kind of reaction, it's going to happen faster. So the number of collisions is controlled by what kind of reactants you have. But something easier to put your hands on would be physical state. Something in solid form is not as accessible as something in liquid or aqueous or even gaseous form. So the rate is going to depend upon different states that you have. For gases, they can be affected by pressure and volume. So you expand the volume, molecules move further apart. How often are collisions going to happen? Not quite as often. So fewer collisions means less rate. Surface area of solids is going to affect the rate. If you have a sugar cube versus a teaspoon of sugar, what's going to dissolve faster? The teaspoon of sugar, because you have more molecules exposed to the solvent that you put it in. Do you have a homogeneous or a heterogeneous mixture? Are the materials mixed amongst each other naturally, or do you have to force them? So the different physical states is going to play a huge role in the kind or the number of collisions that you have. Temperature, third idea, is going to play a rate. Typically, if you have a higher temperature, that means molecules are moving faster, so you get more collisions. Concentration, you have the same number of molecules in a smaller volume, means that more collisions are possible. So it all goes back to the idea of collisions. So in addition to taking a look at what factors can increase the rate, we also have, if you remember these, catalysts will affect rate as well. So you can change the effectiveness of the collision. So you can change the way that which the molecules react. And if you remember, these things are called potential energy diagrams. A catalyst will increase the effectiveness of collision. So it really gives you an alternative pathway, and it does so by lowering the activation energy. So it allows for the reaction to proceed more quickly. Molecules don't have to gain this amount of energy to get over the hump of the reaction. So if we take a look at how we do calculations, let's just look at this scenario here. You've got, over the course of 4 minutes, you have the change in concentration of N2O5. Okay, so you can figure out the rate a couple different ways. Average rate is just the change in N2O5 divided by the change in time. So we can figure out the average rate over the course in 4 minutes. We can figure out the average rate per minute, and you're probably going to see that this is going to change slightly. But so average rate is always the change in whatever over time. You can see that, like I said, if we do it per minute, you can see that the rate is actually slowing down. That makes sense because it's a reactant. We're using the reactants up, so what's left is going to take longer to react. You can also get the overall rate by averaging things together, and you get 0.030 molar per minute. So something you would typically take a look at, what's the average rate of change? You can also calculate the instantaneous rate of the reaction at any particular point by doing a little calculus, integrating the slope, all that kind of stuff. So they're doing the tangent line method, finding the slope of the tangent line will give you the instantaneous rate at any particular time. We're really not going to focus too much in this for this first year in chemistry. But realize that it's possible, and you might be faced with a situation like this either in freshman chemistry or some other place. So taking a look at the relative rates, it requires us to look at stoichiometry. So relative rates means one chemical in the reaction compared to another chemical. So as reactants are getting used up, products are increasing in their rate, and all of this is happening proportional to the mole ratios from the balanced equation. So the rates are relative to their mole ratios. So for example, we've got this general reaction. We see this a lot. You've got the amount of A, the amount of B, the amount of C, and the amount of D in terms of moles. So the rate is really equal to this idea. So the rate of A is equal to the rate of B by taking the numbers of the coefficients over 1. Notice that for the reactants, the rate is going to be decreasing, so it's negative. For products, the rate is increasing, so it's positive. Okay, so if you take a look at this and think about it, if the rate of consumption of N2O5 is 0.05, what's the rate of production? Well, if you think about it, you're making twice as much NO2 as you are using up this. So mathematically, it makes sense that if this is 0.05, this guy should appear at a rate of 1.0 moles per second, or moles per liters per second, rather. But mathematically, you can prove it, set it up. The coefficient is 2 for the N2O5, it's 4 for the NO2. So you do mathematically figure out everything, and you wind up with what we figured out, 0.05 times 2. So the setup of the rate works out to what we logically thought it would. All right, so that ends the first video here. We want to save rate laws for the next video because it's a little more complicated. So we'll end it here, and please make sure you read the chapter sections that go along with this and start some problems.